Okay, going over the homework for Atwood problems. Now, keep in mind at the start of this, before you jump around, hopefully, that this is a challenge homework assignment essentially. Atwood, this is a worksheet that involves all the concepts we've talked about so far. In fact, over half of these are straight out full 15-minute AP free response problems. So it's also a good example of what you may see on the AP test. So for number one, we got a 20 kilogram block on a frictionless table. So one of the things I'm going to try and do is highlight some of the things you should be noting as you go through here. So frictionless table is a very important concept. Hold on, there we go. All right, so a frictionless table here, very important. Cord attached to the block horizontally at the edge of the table. 10 kilogram mass hangs at the end of the cord. Draw and label the force vectors acting on each object. So for object A, we'll do here. Then for object B, we'll do here. So A is, there's going to be gravity. So we'll say we'll label that MAG, and it's going to have normal force, and it has a tension, and that's it, because there is no friction. And then for B, it's just gravity down. Call that MBG, and then there will be tension up. Now notice that I'm making tension smaller than gravity because B is going to accelerate downward. It should be falling, therefore there should be a net force down. And calculate the tension in the cord. So for this one, this really should be, if they wanted to make it easier on you, be a part C, find the acceleration of the system, and then D, calculate the tension in the cord. Because to calculate the tension, you must have the acceleration of the system. The temptation here is going to say, well, if this is a 10 kilogram mass, then this is 100 newtons of gravity down. So it's 100 newtons is the tension up. That would only be true if we're at equilibrium, and we are not. Instead, since this is an Atwood problem, we have to combine the objects. So we have a 20 kilogram block and a 10 kilogram mass. So we have 30 kilograms being accelerated. There's 100 newtons of gravity acting on block B because MBG is 10 times little g, which is 10. And there is nothing to the left because there is no friction. So right minus left, which there's nothing, so you don't have to put a zero there, but some people like to have it, equals the total mass of the system times A. Your acceleration is going to be 3.33 meters per second squared, because that's going to be 100 divided by 30 is 10 divided by 3. Now to find the tension, pick either block. It doesn't matter which. In fact, I'm going to do it with both just to show you that it should not matter and who cares about the mass, or who cares which one. So if we do block B, it would just write out your equation. Up minus down equals MA. So the tension minus 100 newtons of gravity, because again, 10 times 10, equals the mass of block B times its acceleration. Now I'm making it negative because the block will be accelerating down. The acceleration for A should be positive because it is accelerating to the right. This gets me T minus 100 equals negative 33.33. And then add 100 to both sides, and my tension should be, what would that be, 76.67? Now, like I said, if I use block A, I should get the exact same thing, because for block A, it's right minus left equals its mass times its acceleration. Wait, not 76. What am I talking about? 66. Hold on, let me actually use a calculator, because I am clearly too tired to do this right. Yeah, 66, not 76. And if I do 20 times 3.33, I'm going to get 66.67. So it doesn't matter which one you do, as long as you know you add correctly. Problem 2. car whose mass, including that of the occupants, is 1,000 kilograms, is parked 10 meters from the edge of the cliff. Someone ties a rope to the car's bumper and a 50-kilogram rock to the other end of the rope. He then lowers the rock over the edge of the cliff, and the car, which is in neutral, accelerates towards the edge. Nothing like a good old physics of murder problem. Draw a force diagram, label the forces acting on the rock and the car. So if we are assuming the car is in neutral, then we are going to assume frictionless. So for the car, it would be the mass of the car times g would be gravity down. There would be the normal force up. The free body diagrams are going to be exactly the same as the free body diagrams that I had for problem 1. What is the acceleration of the car towards the edge? So again, I'm just going to treat that as, you know what, I have a total mass of 1,050 kilograms being pulled. It is being pulled by a 500 Newton force, and it is opposed by nothing. Where's the 500 coming from? That is the mass of the rock times 10. Is the force of gravity acting on the rock. So the rock is what's accelerating this entire system, the force of gravity acting on the rock. And because there's no friction, I have nothing to the left. So I make my system right minus left, and there's nothing to the left, equals mass times acceleration. And so if I divide both sides by 1050, I get an overall acceleration of 0.48 meters per second squared. And then part C says, how long do the occupants have to apply the brakes before they go over the edge? If they're asking for time, we're back into a kinematics problem. So let me go ahead and change colors here, go with white. So V equals V, V naught equals V equals A equals T equals delta X equals, the car is at rest, one would have to assume. You have an acceleration of 0.48 meters per second squared, and it says they are 10 meters from the cliff. So I want time, I don't care about V, so I use my equation without V in it, which is delta X equals V naught T plus 1/2 AT squared. 10 equals 0 plus 1/2 A T squared. So I'm going to multiply both sides by 2 to get rid of the half. So 20 equals 0.48 T squared. Divide both sides by 0.48. And I get 20 divided by 0.48 is 41.67 is equal to T squared. And I take the square root of both sides, and I get that time is 6.45 seconds. All right. Number 3. We have an Atwood machine, 2 masses attached to a frictionless massless pulley. The mass of block A is 5 kilograms and the mass of block B is 2 kilograms. What is the acceleration of the system when the blocks are released? Okay, so again, look, in the end, we can just simplify this. The A block is 5 kilograms, right? And this is 2 kilograms. So again, just the shortcut is we know this is 50 newtons. Hopefully you take the mass, multiply it by 10 to find gravity is easy enough at this point. So that's going to be 50 newtons and that's going to be 20 newtons. So again, the simplification here is we combine this into one object. The system's mass is 7 kilograms. And there's 50 newtons trying to pull the system one way. And then there is another 20 newtons trying to accelerate the system in the other direction. So right minus left equals the system mass times A. negative 30 equals 7a. And if I take 30 divided by 7 or negative 30 divided by 7, then I get an acceleration of negative 4.29 meters per second squared. By the way, there's really no convention here, at least that we've not learned yet, that matters for this. So the fact that we picked 50 to the left, 20 to the right, basically what I'm saying is I would take either positive or negative for this answer, because I could have decided my bigger forces to, it just doesn't matter. Because realistically, the acceleration of A would be negative 4.29, it's going to fall. B would be positive 4.29, it's going to go up. I would accept either answer. Doesn't matter. How long will it take to fall 2 meters? Now we're back into another kinematics problem. So V naught equals V equals A equals T equals delta X equals. So it says, again, doesn't say it's released from rest, but if it says they're released, you have to assume they're not moving, and they're looking for falling 2 meters. So because I have my acceleration being downward, I need to make sure my displacement is downward as well. We're looking for how long, so this is going to be exactly like the last problem. It's going to be delta X equals V naught T plus 1/2 AT squared. So negative 2 equals 0, because if V naught 0, the whole term is 0. Got my acceleration. Looking for my time. I'm going to go through the exact same steps, multiply both sides by 4 to get rid of the half. Divide both sides by negative 4.29, which means I've done my sign right, because I'm getting I'm not having to take the square root of a negative number. So negative 4 divided by negative 4.29 gets me 0.93 is equal to t squared, and take the square root of both to get my final answer of time is equal to 0.97 seconds. Number 4. I think we're on number 4. 3 blocks. Okay, so yeah, this is one we actually have already done, because I went ahead and put this in the notes for Atwood in the first place, but it's worth doing again. So find the acceleration of the 4 kilogram block. So again, I can simplify this system to be 4 kilograms this way and 3 kilograms hanging over here, because that string does not care if it's a 3 kilogram mass or a 2 kilogram and 1 kilogram mass, or 3 1 kilogram masses or 6 half kilogram masses. It just knows if I cut that string, 3 kilograms is going to fall. So I can simplify that even further into saying, well, the whole mass of the system is 7 kilograms with 40 newtons this way and 30 newtons pulling the other way. Where am I getting 40 and 30? Because the force of gravity on a 4 kilogram mass is 40 newtons, and the force of gravity on the 3 kilogram mass is 30 newtons. So right minus left equals MA. 10 equals 7a, divide both sides by 7, and you get the acceleration of the system as a whole, but also of the 4 kilogram mass, is 1.43 meters per second squared. Now, that's the number. Where you have to make sure you take a look at is, what is the acceleration? It says specifically of the 4 kilogram block. And because the 4 kilogram block is heavier than the other side, the 4 kilogram block is going to fall. Therefore, it has an acceleration that is negative. All right, B. The tension in the string supporting the 4 kilogram block. All right, so now I'm not looking at the whole system. I'm looking specifically at the 4 kilogram block. So for the 4 kilogram block, I would have tension up and the 40 newtons of gravity down. So up minus down equals m times a. So when I want to find the tension, I look just at the 40 kilogram block, and that gets me 4 times negative 1.43 is negative 5.72. And then if I add over 40, I get a tension of 34.38 newtons. And then it says the tension in the string connected to the 1 kilogram block. The easiest way to do that, let me erase the work for part 1. The easiest way to do that would be to just do the 1 kilogram block, which would also be tension up, and it's 10 newtons of gravity down, because again, mass times 10 is gravity, so T minus 10 equals M times A. In this case, it is going to go up because it's the lighter side, so that would be a positive acceleration. T minus 10 is 1.43, add over the 10, and you get 11.43 newtons. The slightly more complicated, but equally valid thing to do would be use the 2 kilogram block if you felt like a challenge, because that would be gravity down. It'd have 20 newtons of gravity down. It would also have, we'll call it T1 down, the bottom string, and it would have T2 up, the top string. So this would be T2 minus T1 minus mg, which is going to be 20 for a 2 kilogram block, equals m times a. It too will go up in the air. And we know that T, what we are calling T2, was 34.38 because we already found it. So 34.38 minus 20 is 14.38 minus T1 equals 2.86. I'm going to add the T1 over and subtract the 2.86, and what I get is 11.52 2 newtons. Now this is different than this one, but not the very. That's just a rounding error, and that's close enough. All right, next up, 2 guide rails for an elevator shown. Again, this is taken straight from an old AP test. Each exert a constant frictional force of 100 newtons on an elevator car when the elevator car is moving upward with an acceleration of 2 meters per second squared. The play has negligible friction and mass, and assume that G is 10. Draw and label all forces acting on the elevator car. So what we would have is gravity. We would have tension. And then also, if this is being pulled up, we have 2 forces of friction. And this is where people screw it up. It says the 2 guide rails on the elevator shown each exert a frictional force of 100 newtons on the elevator car while it is moving upward. So each means 2 forces of friction, and friction acts opposite of motion, so it would be down. Identifying the source, the tension would be from the cable, gravity would be from the earth, and friction would be from the guide rails. B, calculate the tension in the cable lifting the 400 kilogram elevator car during the upward acceleration of 2 meters per second squared. So that's up, minus down, minus down, minus down equals MA. So the tension minus 100, because it tells you each frictional force is 100 newtons, minus the mass of the car, which they say is 400 kilograms, times G, equals the mass times A, which they tell you is 2 meters per second squared upwards. So we have T minus 200, I just combined the 2 minus 100s, minus 4,000 equals 800. So add over the 200, I get T minus 4,000 equals 200. Equals 1,000. and then add over the 4,000, and I get that the tension must equal 5,000 newtons. C, calculate the mass m of the counterweight must have to raise the elevator car with an acceleration of 2 meters per second squared. There are two ways to go about this problem. So we will go with the easy way first. This is only easy because we already had to do parts A and B. And that would be for the counterweight, it should have tension up, gravity down, and its tension minus its gravity should equal its mass times acceleration. I suppose technically, to stay with the convention in the problem, I should go with capital M's. Okay, so we know the tension is 5,000 newtons. We want to find the mass, and we know it should be falling at 2 meters per second squared. So what this is 5,000 minus 10m equals negative 2m. I add 10m over, and I get 5,000 equals 8m, because 10, negative 2 plus 10 is 8. And then if I divide both sides by 8, I think the answer ends up being 625. Yep, 625 kilograms. No, I did not do that in my head. I've just done this problem, a couple dozen times in my life. That's the easy way to do it based on the fact that we already knew the tension and we already knew the acceleration and all of that. The other way we could do this problem, that in this particular case is harder, but if we were given this just the problem and the first thing it asked was, hey, if the acceleration is 2, what's the mass got to be? The other way you could do is treat this as one object, because the mass and the elevator car are going together, with a mass of 400 plus m. It's being pulled mg this way, and it's being pulled 4,200 newtons this way, because you got the two frictional forces acting this way as well. So it would be mg minus 4,200 equals 400 plus m a, and then from here, we know the acceleration's 2. And so from here, it would just be solving a problem. So mg minus 4,200 equals 800 plus 2m. I could just do 10m here because, g is 10. Whoops. And you should be able to notice that we're quickly getting what we're going to get on the right, because I add the 4,200 over, I subtract the 2m, and I get 8m equals 5,000, which is going to give us, again, 625 as my mass. So either approach works. All right, ultra low friction pulley as shown. The two weights experience an acceleration of 0.45 meters per second squared. Find the mass of the second weight. So there are a couple of options here. The easiest one would be what I just showed as an alternative for the last problem, which is, hey, I've got some mass. That's not an M. I've got some mass plus the mass of that block. This block is getting pulled with a force of 10.8 newtons, because again, gravity down is going to be mass times 10. And this unknown mass is getting pulled with mg, whatever that is. So right minus left, I turned it into 10m because g is 10, equals your total mass times your acceleration, which we know is 0.45. I can distribute the 0.45, so do 0.45 times m plus 1.08 times 0.45 gets me 0.486. Subtract 0.486, add over the 10m, and I get 10.8 minus 0.486 gets me 10.31 equals 10.45 m, and then divide both sides by 10.45. And I get a mass of 0.99 kilograms. Now, your sanity check here would be, it says it's accelerating upward, right? So what that means is this side has to be heavier than this side. Otherwise, it's not going to move, or it wouldn't be accelerating upward. And the mass we found of 0.99 kilograms is less than the 1.08 kilograms on the right. So the left block would move up. They're also pretty close, so it makes sense that your acceleration should be fairly small. Like if you wound up with like 1 kilogram and 1/10 of a gram, you would expect that thing to go rocketing. But they're relatively close, and that gives you a relatively small acceleration, which you should expect. Next up, 3 masses are connected by a light string that passes over a frictionless pulley. What is the acceleration in the system, and what are the tensions of the string? This is exactly like the 4, 2, and 1 kilogram mass problem before. So I'm going to treat this all. This side of the problem, or this side of the system, has 65 newtons pulling down because mass times 10. This side is going to have a total mass of 6.45 kilograms, which means it'll have 64.5 newtons pulling down. So that's pretty close to the same mass on each side. I should expect to get a fairly small acceleration. So this is a total mass of 12.95 kilograms, because that's just the total mass added up. So 4.05 plus 2.4 plus 6.5. And I've got 65 newtons pulling on one side, and I've got 64.5 newtons pulling on the other side. So it's right minus left equals m times a. 0.5 equals 12.95a. Divide both sides by 12.95, and I should get a remarkably small number. A equals 0.039. And that says, what are the tensions in the string? I'm going to guess strings, plural, both of them, because I'm guessing we'll call this one T1 and this one T2. So the easiest way to do it is to find T1. I'm going to make my system just the right mass, because for the right mass, it's T1 up with 65 newtons of gravity down. So it's T1 minus 65 equals m times a, which is negative 0.039, because it's going to accelerate downward. So T1 minus 65 equals negative 0.25, and then add the 65 newtons over, and I get that T1 is equal to 65.25 newtons. Likewise, to find T2, I'm just going to look at, whoops, I chose the wrong color to highlight on white. I'm going to just look at the left one, the bottom one. Now, the reason why I'm doing that is this one here, the upper one, has both tensions acting on it, so the force diagram is more complicated. The ones that only have one string acting on it, it's just tension up, gravity down, T2 minus mg, which in this case is going to be just 2.4 times 10, or 24, is equal to mass times the acceleration, and that's going to be an acceleration upwards. So T2 minus 24 equals 0.0936, and then I'm not dividing anything. I'm adding 24 over to the other side, and T2 is equal to 24.09 newtons. Last problem, and this is a fun one. This is the devil problem. All right. We got a ramp system with a 7 kilogram mass attached to a 6.5 kilogram mass by a light string that is threaded through a low friction pulley. The 7 kilogram mass accelerates up the ramp when the other mass is released. Draw a free body diagram and find the acceleration if the coefficient of friction between the 7 kilogram mass and the plane is 0.28. This problem has it all. It's got ramps, it's got Atwood, it's got friction, it's got something for everyone. So let's draw the free body diagrams. We have gravity straight down. I'm going to call this M1G because this one also has gravity straight down. Call that M2G. This has a normal force acting perpendicular to the surface. It has a tension up the ramp, and it has friction down the ramp. Whoops, I'm sorry, I mislabeled that. This one up the ramp should be T, not F. My mistake. This one should just be T. Okay. So step one, we're not at equilibrium because we're looking for an acceleration. Step two, we drew the free body diagram. Step three, we need to break gravity up into components because we are on a ramp. So this is mg y, and this is mg x. This is going to be 70 newtons, and this is a 35-degree angle. So I'm going to do the trig at the end. In fact, I'm probably just going to do the trig in the problem itself because why not? All right. So next up is writing an equation. Now I am going to go ahead and I am going to draw a new free body diagram for the block on the ramp just to clear everything up. So I've got tension up the ramp, I've got friction down the ramp, I've got a normal force up, and then I have a y component of gravity down, and I have an x component of gravity to the left. Okay, so this is where it's going to get fun, because what I need to know is I need to know mgx and I need to know friction. So if I were to go straight to simplifying this problem, like gravity here is simple, it's 65 newtons. That's nothing. So if I go straight to simplifying this problem, which simplifying this problem would be saying, listen, what I've really got here is a total mass of 13.5 kilograms, right? Because that's 7 plus 6.5. I've got 65 newtons this way. Well, this way, I've got mgx and I've got friction. So if I try writing out this equation, it's 65 minus mgx minus friction equals my total mass times my acceleration. I got some stuff to find. Now I can find mgx because mgx is going to be 70 sine 35. Now, where did the 70 times sine 35 come from? It's my hypotenuse, which is going to be my mass of 7 times 10. And then because I'm looking for my opposite side, it's sine of 35 equals mgx over my hypotenuse, opposite over adjacent, and I multiply the 70 over. And then I went ahead and replaced friction with the equation for friction, because don't forget our equation for friction is friction equals mu times the normal force. Okay. But I need to find the normal force. So what I need first is my equation in the y direction, normal minus mgy is equal to 0 because I'm not accelerating away or into the ramp. I'm accelerating up the ramp. So that's going to be normal minus 70 cosine 35. Or my normal is equal to 70 times cosine of 35. Because again, I want my adjacent side, and adjacent is, or cosine 35 is adjacent over hypotenuse. So I multiply the 70 over. So if I actually plug that into my calculator, I get normal force is 57.34. So if I start going from here, 70 sine 35 is 40.15 minus my coefficient of friction, of kinetic friction, times my normal force, which I just found was 57.34. And if I multiply those two together, I get 65 minus 40.15 minus 16.06 equals 13.5. If I subtract all that stuff on the right, I get 8.79 equals 13.5a. And if I divide both sides by 13.5, I get an acceleration of 0.65 meters per second squared is my acceleration. If you can do that problem, you can do any problem in this unit. It has everything.